Fields are magnitudes defined at all points of space and time. These magnitudes must transform in a well-defined way under the Poincare group, because otherwise it would be impossible to construct Poincare invariant laws for their dynamics and interactions. In practice, only the Lorentz part of the Poincare group is relevant in this problem, and these well-defined transformations under the Poincare group means that they transform in linear representations of the Lorentz group. So fields belong to linear representations of the Lorentz group. Of course, we are talking about relativistic fields because non-relativistic fields do not have to satisfy these properties. These linear representations are of two kinds. They are tensorial representations or spinorial. Although there can be mixed representations. Those that transform in these tensorial representations are called tensors, and we have seen how tensors transform, covariant, contravariant, or R times covariant and S times contravariant. And the spinorial fields that transform in spinorial representations are called spinors. Okay, and there are also, just as tensors can be sometimes understood as products or simpler representations, vector and differential form representations, there are representations that can be understood as products of the simplest spinorial representations. We are not going to deal with spinorial representations here because they are not easy to generalize to the gravitational context. It is possible to do it, and it is necessary to do it because certainly spinors will move in curved space-time and will feel gravity, but this mathematically is much more complicated to deal with them, so we will not treat them in these basic curves, and we will focus on these tensorial fields. Okay, in nature, the fields that we have are either scalar fields. Okay, for instance, the Higgs field, we know that they transform as just functions, vector fields, or actually differential form fields. So such as the electromagnetic field or the Young-Mills fields and the metric field that represents gravity. This is the simplest version, but of course there are subtleties because fields which transform as a scalar with respect to the Lorentz group can have additional freedoms, and they can transform in some other ways under some other internal symmetry groups like Young-Mills gauge groups. The same is true about vector fields, but it is not true, or also about the spinorial fields, but it is not true about the metric field. The metric field only has these geometrical symmetries, so it only transforms non-trivially under the Lorentz group in the context of special relativity and under transformations of coordinates in the more general setting. So what we want to do in this section is to study all these fields, find their transformations under the Lorentz group, see how to construct Poincare invariant actions for them that are physically well suited to describe their dynamics, and find the associated conserved quantities to the symmetries that you have, the simplest interactions, and so on. In particular, we will be very interested in interactions with point-light particles because we have studied the action for point-light particles before, for massive and massless, and we have found equations of motion, and it will be interesting to see how they are modified when we couple them to these fields. Let us start by saying some general things about the construction of relativistic actions for relativistic fields. So now the action for some relativistic fields, which I represent generically as this phi, instead of being an integral over time that can never be relativistic invariant, will have to be integral over this d4 dx4, which is by definition the product of this differential. So it is a volume 4 volume integral dx0 dx1 dx2 dx3. This we can call d3x. This would be a standard spatial volume, and then the time of some function constructed with the fields and derivatives, but the derivatives not just with respect to spatial directions, but with respect to all the directions, including time. So this represents partial mu of phi. And in general, we will ignore the possibility that there are terms with second derivatives of phi. I don't know if I have used this notation before, but partial mu of phi indicates it's the same as this. Okay, so it's a shorthand for this. This function is usually called the Lagrangian density, or Lagrangian, just Lagrangian. So we will call it just Lagrangian. Okay, and then if I split this integral as an integral over the x0 and then an integral over the volume, and this Lagrangian density, if you want, some people call this thing the Lagrangian L, but we will not use these names. Okay, we will call L the Lagrangian. Now, the requirement of Poincare invariance of the action means that when we perform a transformation of the coordinates of this form, the action has to be invariant. So let's start seeing how the volume element d4x transforms. And I need to introduce some notation for this, which is very convenient because we will use it later. Okay, so let me write this d4x in an alternative form, and this alternative form will be this dx sigma. What is this epsilon mu nu rho sigma? Okay, I start by explaining what epsilon mu nu rho sigma is. The parentheses denote a tensor, and this is a completely antisymmetric tensor. So if I interchange any two indices, I will get a minus sign. This is similar to the epsilon I j k symbol in 3 dimensions, but now I have 4. So completely antisymmetric. And this means, by the same reasoning that we did when we dealt with epsilon I j k, this means that it can only be different from 0 when all the 4 indices are different. So, and I fixed one of the components, 0, 1, 2, 3, in this order to be plus 1, and the rest of the non-vanishing components are obtained by interchanging these indices. So, for instance, the epsilon 1, 0, 2, 3 is minus 1, and so on. And if an index is repeated, then I get a 0. Okay, so this determines completely this epsilon symbol, which is also known as Levi beta symbol. What is epsilon mu nu rho sigma? Okay, it is the tensor that I get by lowering the indices of epsilon mu nu rho sigma with the metric eta mu alpha, eta mu beta, eta rho gamma, eta sigma delta, epsilon alpha beta gamma delta. Now you see that if I want to, first of all, it is completely antisymmetric because epsilon is completely antisymmetric. You can check this. Then again, I only need to give the value of one of the components, epsilon 0, 1, 2, 3. So this will be, according to this relation, eta 1 alpha, eta 0 alpha, eta 1 beta, eta 2 gamma, eta 3 delta, epsilon alpha beta gamma delta. And now this is an important formula that you have to know. This is by definition, if you want, the determinant of the matrix eta, and the determinant of this matrix is -1. Okay, so with indices down 0, 1, 2, 3 has a -1 here, and this is the reason why I have added this -1. Now let's see the reason why we have this 1/4 factorial. This is summed over all mu's, nu's, rho's, sigmas, so it contains, among other terms, 1/4 factorial epsilon 0, 1, 2, 3 dx 0, 1, 2, 3. Okay, I don't write the full expression, but also all the permutations. So epsilon 1, 0, 2, 3 dx 1, 0, 2, 3, and so on. If I take this in all the terms in this way, since this dx compute the way that I have written them, this will be minus this one, but this will be exactly the same as this one. Okay, so there is a minus, but this is related with a plus, and then I would get 0. So something is missing here. The thing that is missing is a wedge product, which is a product that I don't know, we will have time to explain. That is completely antisymmetric. So when I interchange two of these differentials, I get a minus sign. Okay, this is part of the formalism. So indeed, this would be wedge, but customarily this is omitted. So this is why I haven't written them. When you write d for x and you expand it as dx0, dx1, dx2, dx3, you don't write these wedges, but they are there. And in a more complete or rigorous expression like the one I have written here, you have to write these wedge products. Just don't ask what they are right now. They are just something which is antisymmetric. This means that instead of a plus, when I interchange these indices here, now it is interchanging two of these differentials and I get another minus sign. So I get always a sum, because I get the same permutation here and here. So I get a sum over all the possible permutations of these 4 elements, and these are 4 factorial. So this will be minus epsilon 0, 1, 2, 3 dx0, dx1, dx2, dx3, and we have seen that epsilon 0, 1, 2, 3 with the indices down is -1, so this cancels this, and this is the d for x that we have written. We have done this exercise because now it is a lot easier to see what is the transformation of the volume element under the Poincare transformations. So how does dx mu transform? Well, it is just we have to differentiate here and you get lambda mu nu dx nu and nothing else because the a mu's are constant. If I plug this into the formula, so we have epsilon mu nu rho sigma, this thing is just invariant, okay? So we have 1 mu alpha lambda nu beta lambda rho gamma lambda sigma delta dx alpha dx beta dx gamma dx delta and minus 1 over 4 factorial if you want. Okay, so how much is this? Okay, remember what we said about the determinant. So here we are summing over all the possible alpha, beta, gamma, deltas because this is antisymmetric, no two indices can be repeated, etc, etc, etc. So there are 4 factorial terms of the form dx0, dx1, dx2, dx3 and this epsilon. So this gives minus epsilon mu nu rho sigma lambda mu 0 lambda nu 1 lambda rho 2 lambda sigma delta dx0 dx3. And as I just said, this is nothing but minus the determinant of lambda, and it is minus because the difference between this formula that I applied here and this here with epsilon up and epsilon down is just the overall sign. So this gives me minus determinant lambda, and then this term cancels with this, so this will be the determinant of lambda times what I call d for x. Now the determinant of lambda for proper Lorentz transformations, okay, is plus 1. So this element is invariant. I suppose that you know that the determinant of the Lorentz transformations is either plus 1 or minus 1, but I just need to check this. I just need to go to the definition of Lorentz transformation. Remember that they preserve eta. If I write it in matrix notation, which is better, I write it like this. So I take the determinant of both sides of this relation. Sorry, determinant of eta, I know that this is minus 1, and this is the determinant of lambda squared. The determinant is the product of the determinants. The determinant of lambda transpose is the same as lambda, so this is the determinant of lambda squared times the determinant of lambda, sorry, of eta, which is also minus 1. So you conclude that the determinant of lambda is either plus or minus 1. Okay, with a plus you have what you call proper Lorentz transformations and improper. These are connected to the identity, but these are not. These correspond to the product of a proper Lorentz transformation by, for instance, a time reflection in which you invert the sense of time. And we will restrict ourselves to these ones. These transformations, you can say that they change the orientation. You change the sign of one coordinate, or you interchange 2 coordinates. And although this is not usually said, this volume element contains dx0, dx3 contains an implicit order. So we have defined this to be dx4, the 4 volume element, and not in any other order. Okay, this is an orientation of the space, and volumes are computed with respect to that orientation. If you interchange 2 of these differentials, or changing the sign of one of them, you are changing the orientation. You get volumes with negative sign and so on. So this is why we are going to consider only proper Lorentz transformations that preserve the orientation and have determinant plus 1 and leave invariant the volume, integration volume dx0, dx3. Proving this without using this Levi-Civita symbol is more difficult, much more difficult. In any case, the conclusion of this exercise is that if S is going to be Poincare invariant and d for x is Poincare invariant itself, L must be Poincare invariant. Poincare invariance of the Lagrangian will be one of the main hints that we will use, or one of the main constraints that we'll use to construct Lagrangians for relativistic fields. Now, the main use of the action in the classical context will be to find the equations of motion. For this, we need to devise some principle of least action, some generalization of the principle of least action in this field theory setting. Okay, so first of all, we have to be a bit more precise with the action. Clearly, we have to be integrating on some volume V4, and this volume will have a boundary that is denoted by delta of V4. And the setup will be that we consider fields phi x, or field configurations phi of x, which have a prescribed value on this boundary. So when you restrict them to the boundary, they take this prescribed value, and okay, these x's are only defined on the boundary. So in the points in the boundary, there is some function phi 0, or whatever field configuration phi 0 in the boundary, and this is the value that we prescribe for all these fields. Then we are going to demand, or to adopt the principle that the physical configuration that the field will take will be the one that minimizes the action. Out of all of the phi x's that satisfy this boundary condition, and that you can plug into this action to give you a number, the one that extremizes S and principle minimizes it will be the one physically realized. So if phi x is this physical configuration that we want to find, when we consider other configurations which are close to it, so they differ by some small piece delta phi x, the idea is that this action will remain invariant, at least to first order. Okay, this delta phi x, because this modified configuration must still be one of the ones that satisfy this boundary condition that we have imposed on all of them. This means that this delta phi on the boundary must vanish. So this is the boundary condition that the delta has to satisfy. As you see, you can see the analogy with the mechanical cases. In the mechanical case, instead of V4, we have an interval of integration between T0 and T1, or lambda 0 and lambda 1. And at those 2 points, which are the boundary, you impose on the variables, on the mechanical variables, that they take a certain value. Since these are 2 points in the mechanical setting, then this phi 0 is just a constant. However, the boundary of a 4-dimensional region in general is a 3-dimensional space, and these prescribed values will be given by some function defined on this 3-dimensional space. About the deltas, okay, we also impose there that the variations that we consider are vanished on the boundary, which was T0, T1, or lambda 0, lambda 1. Here we impose that they vanish on the whole 3-dimensional boundary. And okay, to make the story short, we just vary the action, okay, to find the term which is proportional to delta phi, because that will be what we call delta s over delta phi, and its vanishing will be the equivalent of the extremization of a function. Okay, delta s over delta phi is like the first derivative of a function taking the value 0 near an extreme. So we vary delta s, and as in the simple mechanical cases, these transformations of these deltas do not act on x. So therefore x is invariant, and the only thing that may change is L, because it depends on phi and delta phi. Okay, so this variation will be okay, now we take the derivatives with respect to phi and delta phi. This is essentially the chain rule, and also the derivatives of phi and delta of the derivatives of phi, and nothing else, because we have assumed that delta does not depend on higher derivatives of phi and does not depend on just functions of x, so there is no explicit dependence on the coordinate either. And okay, in order to find something only proportional to delta phi, you have to do something with this term. Since delta does not act on the coordinates, the partial derivative with respect to coordinates commute with delta, and this will be equal to partial mu delta phi, just as we did in the mechanical case. And next we must integrate by parts. So this first term stays as it is, delta phi plus, now we have this partial mu acting on partial L with respect to partial mu phi, and delta phi minus partial mu partial L with respect to mu phi and delta phi. So far nothing new. I collect the terms which are proportional to delta phi, minus delta phi, and then I have this term which is the analogous to the total derivative with respect to time that we had in the mechanical case. But now it is clearly quite different, because we are in a 4-dimensional context instead of on a 1-dimensional context. So how can we treat this term? Okay, you have to use this 4-dimensional version of Gauss theorem. So Gauss theorem in this context says that if you have the integral of something like this, and this something like this is a set of partial derivatives contracted of a vector with the indices contracted. So instead of mu and nu and something like that, you have this contracted. This is called the divergence. Okay, this is then equal to the integral over the boundary, which is, remember, 3-dimensional, of now you have the 3-dimensional volume element of the surface, and okay, I will draw you a picture of this. Remember that in the standard application of the Gauss theorem, you have a 3-dimensional volume, then the boundary is a 2-dimensional surface, and this 2-dimensional surface is characterized by a vector normal to the surface. So you can decompose this d2 sigma I, this could be what you have in this 3-dimensional context, or d2s I, usually you represent it as d2s, an element of integration over the surface, and the components of a vector normal to the surface. This is entirely analogous. This can be decomposed into the 3 sigma and a vector, now it's a 4 vector, which is normal to this 3-dimensional hypersurface. A hypersurface is a subspace of the total space which has 1 dimension less than the total space. This is usually expressed as codimension 1, and this is what you expect of the boundary of a 4-dimensional volume, that it is a hypersurface or a space of codimension 1, and this would be the integral. Okay, now depending on the orientation of this 4 volume, you will get in general a particular orientation of this 3-dimensional volume and this vector. So this vector is pointing outwards, but in a 3-dimensional space this is a bit more difficult to define. However, we are not going to need this because, okay, let's focus only on this term. So we are integrating everything over before, although I am forgetting to indicate it. So we have the integral of partial mu and this partial L partial mu phi delta phi, and using this Gauss theorem, okay, that I put in this box. So if we use it here, this is going to give you an integral over the boundary of the volume of the hypersurface partial L with respect to partial mu phi delta phi. Now, of course, when you integrate, you evaluate the integrand over the whole space of integration, and the boundary condition that delta phi satisfies is that over this volume of integration, which is now this boundary, delta phi vanishes. So this is automatically 0 thanks to these boundary conditions. And because this is 0, we just find a term which is proportional to the variation of phi only. Okay, this is what then by definition we will call ds d phi, and if this is 0 because phi of x is an extremum of this action, then delta s over delta phi has to be 0. Okay, and delta s over delta phi, which is partial L partial phi minus partial mu L partial mu phi equal to 0 are the equations of motion, and these are the Euler-Lagrange equations in this field theory contest. Now, if these are the equations of motion, if phi transforms in a representation of the Lorentz group, it should be more or less obvious that these equations will transform in a well-defined way under the Lorentz group, which means that if they will be form invariant. What happens if L depends on derivatives higher than 1, derivatives of the fields higher than 1? Okay, you go through the same steps and you find that you have to add terms of this form. So if you have second derivatives, you would have two derivatives like this, a term like this, then a term with three derivatives, and so on. Okay, this is what you would find. Finally, it is not so difficult to check that if you have an action that differs from the original one, or a Lagrangian that differs from the original one by a total derivative, and here a total derivative is, instead of just a total derivative with respect to time, it's a divergence of some vectorial expression, something that has contravariant index, then the equations of motion that follow from S prime are the same that follow as those that follow from S. So delta S prime over delta phi is equal to delta S over delta phi. Okay, and so this is the kind of terms one can add if one finds it convenient, or remove. At this classical level, okay, there are always subtleties with these operations, but from the point of view of finding the equations of motion, which is the only thing that will concern us from the moment, is perfectly okay to take them, to add them or remove them.